Welcome back to Differential Calculus. Finally, in this video, we arrive. When I introduced the idea of the limit several videos ago, I told you that the goal of this was to develop a tool for codifying what we mean by a continuous function. And now, in this video, I'm going to do just that. Let me get my head out of the way and let's jump right in. A function, and I'm going to name the function f. I'm going to stress that it is a real valued function of one real variable. And we're going to say that it's continuous at a point c, a real number c, if and only if three conditions. F of c is defined. The limit as x approaches c of f of x exists, and the limit as x approaches c of f of x is in fact equal to f of c. All three of those things must be true in order for us to say that the function is continuous at the point. If any one of those three things is not true, then we can immediately say that the function is not continuous and not have to worry about anything else. In some references, especially if you look at higher level mathematics, we really only look at the third condition here. The other two are implied by that third condition, right? If it is the case that f of c is defined, then we have a number to plug in here. If it is the case that f of c is not defined, then we don't have a number to plug in here. If it is the case that the limit on f of x exists, then we have a number to plug in here. If this limit does not exist, we don't have a number to plug in here. And does not exist and undefined, I have stressed a couple of times, mean different things. And so we could just focus on that third rule and it would do the job. It would do everything we need it to do. But it's generally going to make our lives easier to think about this as three separate pieces. If we are looking at the function and we try to evaluate the function and we can't do it, immediately the function is not continuous. We don't have to think about anything else. If we're trying to evaluate the limit and the limit does not exist, immediately the function is not continuous. We don't have to do anything else. Only when those two things give us values do we go to that last step and compare those values to see what happens. Before we get to examples, I do want to extend this definition just a little bit, because continuous at a point is kind of nonsensical from the definition of continuity that you learned in your previous courses, right? The function is continuous if you can draw its graph without lifting your pencil. If we only have continuity at one point, that's nonsense. A function is continuous on an open interval if and only if it is continuous at every point. In that interval. And finally, a function is continuous everywhere. if it is continuous on the open interval from negative infinity to positive infinity. Those two definitions are the way that we tend to use the idea of continuity. We can test continuity at a point, but knowing continuity at a single point is essentially worthless to us. We cannot directly test continuity on an interval, but continuity on an interval is the thing that we care about. And in calculus, we tend to deal with relatively simple functions, and a great definition of relatively simple functions is they have a nice definition and they are continuous everywhere. Right? A nice definition, another thing I don't have a great definition for. The easier it is for you to understand the definition by looking at it, the nicer the function is. A problem of a type that you have probably come across in a previous course. Let's find a value for a so that the function f of x given piecewise, ax plus 2 if 0 less than or equal to x is less than 5, and 10 if x is greater than or equal to 5, is continuous on the interval from 0 to infinity. Notice that for negative values of x, this function is not defined, so we cannot talk about continuity at all real numbers. We cannot talk about continuity at the point x equals 0 because there's nothing on the left to analyze to take a limit of. We could extend the definition of limits and continuity to make that a little bit easier, but we don't need to, so I'm not going to. Again, you've probably done something like this in the past, and what we're going to do here is not really any different from what you've done in the past. It's going to look more complicated, but I am again relying on that idea. I want you to get comfortable with talking about limits. If we can make sure that we're comfortable talking about limits on relatively easy problems, then when we get to relatively harder problems, we know what we're doing and we don't have to worry so much. All right. So in order for this function to be continuous, we need to make sure that the function is defined. We need to make sure that the limit exists, and we need to make sure that the limit is equal to the value of the function. And our pieces of the piecewise defined function are a linear function. Linear functions are always continuous everywhere. We don't have to worry about that. A constant function. Constant functions are always continuous everywhere. We don't have to worry about that. The only thing we have to worry about is that there is a break. And so we need to make sure that at x equals 5, so we need to figure out what is the value of f of 5, and the value of f of 5 is 10. We need to figure out what the limit as x approaches 5 of f of x is. And we see that this is a different function on either side. So we have to break it down and look at the one-sided limits. The limit as x approaches 5 from the left of f of x is the limit as x approaches 5 of ax plus 2, which is going to be 5a plus 2. Then the limit as x approaches 5 from the right of f of x is going to be the limit as x approaches 5 of 10, which is just 10. We need the limit to exist. And the limit only exists if these two things are equal to each other. Which tells me that a must be the fraction 8/5. And we can see just by looking at the right-hand side that this is going to work. But ignoring that and just saying, okay, well, a is 8/5. Plug that in over here. We get 5 times 8/5 plus 2, which is 10. Over here, we get 10. So the limit as x approaches 5 of f of x is equal to 10. We get 10 when we evaluate the function. We get 10 when we evaluate the limit. The function is now continuous. And the answer is that the function is continuous when a is equal to 8/5. Again, probably just the part that is now behind my head, set the two pieces equal to each other and solve for the unknown variable. That's the sort of thing that commonly shows up in algebra or pre-calculus courses. So you've probably seen that sort of thing in the past. The difference here is all of the language around the limits. Did we need all of this language? Honestly, probably not. If you saw this in the past, you know that you were able to do it without using the language of limits. We're going to be looking at the same sorts of questions moving forward, looking at more complicated situations involving continuity and differentiation and some of the other tools we're looking at. So having this familiarity now is going to make your life easier later. This one's a little bit tougher, but it's really not that bad. So I want you to see if you can think about it on your own. I want to identify any possible discontinuities and test those points, and only those points, for continuity in the piecewise defined function g of x is equal to x squared minus 1 if 0 is less than or equal to x is less than or equal to 1, x minus 1 over x if 1 is less than x is less than 5, and 0 otherwise. Right, so we have a three-piece function. Some of the pieces are fairly straightforward. Some of the pieces are a little bit messy. G of x is equal to x squared minus 1. If 0 is less than or equal to x is less than or equal to 1. G of x is equal to x minus 1 over x. If 1 is less than x is less than 5. And g of x is equal to 0 otherwise. So, using all the tools that you have from previous courses on how to identify when a function is continuous or not, apply those here. Identify any points where you might be suspicious that the function is discontinuous, and use the limit definition of continuity to either show that the function is continuous at that point or show that the function is discontinuous at that point. All right, take a couple of minutes to play around with that one, and I'll see you in the next video.